What is all this? I just don't understand any of it.
Don't worry, I can help you. Come with me. Here, spinning in 3D, is the crystal structure of a MOF. MOF 5 to be specific. It looks confusing now, but soon you'll know exactly what you're looking at. Let's take a closer look at how MOFs are built up. A MOF, or metal organic framework, is, as suggested, built from both metallic and organic components, which are referred to as secondary building units, or SBUs. Shown here in cartoon form is the metal SBU and the organic SBU, which is also referred to as a linker. Now they combine to form the framework. This is just one simple combination and it extends out in 3D from here. Here you can see the porous structure is generated. Many of the structures become more complicated than this, but this is the basic principle in which they're all formed. So you can see how the pores are formed, and it's periodic and crystalline. Let's look at some of the example SBUs which are used. We're going to start by looking at ZnO4 tetrahedra, with each zinc also coordinating the organic linker. The linker is a para-benzene dicarboxylic acid derivative, or terephthalate. These form MOF5, which is also known as isoreticular MOF1, EMOF1, and it's the first in a series of the same topology but different sized pores. Next up we have a dicopper based SBU and a tricarboxylic acid linker. These form HKUST1, which has been commercialised and is sold under the name Basilite C300 by BASF and is currently £294 for 10 grams. Based on the same dicopper metal SBU but using a much larger and more complex linker, which has multiple benzene rings in, you can form NOT 112, a MOF with a surface area of 3,800 meters squared per gram, which is utilised mostly for hydrogen storage and has proved very promising in this area. Here we have the 3D structure of MOF5 again, but showing more unit cells. Look for the benzene-based linker and the zinc-based tetrahedra to see how it's built up from these two SBUs. Here we have the spinning crystal structure of HKUST1. Look for the dicopper SBU and the benzene-based linker. Try to spot the water coordinated to the copper in this one. Here we have NOT 112. This adopts a more complex shape, but again try to spot the metal SBU and the much larger linker in this one. And try to look at the different sized pores in this particular structure. So what can we do with MOFs and their miraculous structures? Well, they have promising applications in catalysis and may be applied in chemical plants, not only due to their high surface areas, but due to the fact that the metal is readily accessible. They're also showing promise in the sorting and cleaning of exhaust gases from power stations and chemical plants, and may be of use here too. You see those lorries driving by? One day these could all have a MOF-based fuel tank. BASF have equipped lorries which run on natural gas with MOF-based fuel tanks, and they can go up to 30% further on one tank. This is because MOFs are really good at storing gases due to their incredible surface areas, and they're being implemented all over to reduce the use of high pressure systems and improve the gas storage capability. There are many other uses too, which are just being discovered and developed now. It's a new and ever evolving field.
Thank you. Now I understand all about MOFs.